Okay, in this video we're going to cover section 8.2 of the textbook. The title of this section is Review of Power Series. This entire section should be a review of material that you already know from Calc 2. Now, some of it you may be rusty on. Maybe you took Calc 2 somewhere else, and in that class they didn't cover some of these things. Wherever you find deficiencies, you want to go back quickly and review that. Pull out your old calculus textbook or some other resource and find the parts of this section where you're struggling or where you really don't remember what's going on and review those. Okay, so first of all, what is a power series? A power series is, well, it's a series of the form sum as n goes from 0 to infinity of an times x minus x0 to the n. x0, this number here, is what we call the center of the power series, or it's a power series about x0. A power series has something called a radius of convergence, which we'll denote here by the letter rho, lowercase Greek letter rho. Okay. We have that our power series is absolutely convergent for any x in the interval from x0 minus rho to x0 plus rho. So you want to plug an x into that power series, and then you get an ordinary series. When you plug when an actual number in for x, you have an ordinary series, which could be absolutely convergent, conditionally convergent, or divergent. And what we know is that if we put any x that is a distance of less than rho away from the center, then we have an absolutely convergent series. And we have a divergent series for any x that is not in the closed interval from x0 minus rho to x0 plus rho. So if you plug an x in there whose distance from the center is greater than rho, then you have a divergent series. And then what's left after those two cases are, well, what happens if you plug in one of those endpoints? In other words, what happens if I plug in an x value which is exactly rho away from the center? Well, then you don't know. You have to check on a case-by-case basis what's going on. So it may or may not converge at the endpoints of that interval right there. Okay. All right, so that's the radius of convergence. One of the most common tests for convergence, and one that we'll be using a lot here in the coming things that we do, is the ratio test. The ratio test says the following, that if the limit as n goes to infinity of absolute an over an plus 1 exists and equals some number, then the radius of convergence is rho equals L. And here we allow L to be any, well, because of the absolute values, L can't be negative, any non-negative real number. We also allow infinity. So if that limit, in fact, does not exist, but that it diverges to infinity, we say that the limit is infinity, that means that the radius of convergence is infinity. A radius of convergence of infinity means that the power series is absolutely convergent no matter what x value you put in. And a radius of convergence of 0 means that it is divergent for every x value except x0. Notice that if you plug in x0 for x in a power series, then what do you get? Well, you get a0. One way that you can see that is, if you write your power series informally as a0 plus a1 x minus x0 plus a2 x minus x0 squared, and so on. It's informal because I've got 3 dots there. That's a common way for us to write things. We're leaving it to the reader to infer the general pattern that's there, but it is informal, right? The sigma notation is the formal notation that is completely unambiguous. The reader is not required to try and infer some implied pattern. But if I write it informally like that, it might be easier to see what happens when I plug in x equals x0. If I plug in x equals x0, then all of those terms vanish except for the first one, because the first one is just the constant a0. And so, in fact, the series is convergent when you at the center. It's convergent at the center no matter what, always. It's always the case, and it always converges to a0. So radius of convergence of 0 means that that's the only x value you can plug in. Okay, so that's the ratio test, and we allow 0 and infinity there, and the ratio test still gives us information in those cases. Now, another fact, important fact about power series, one that we're going to need in order to do what we want to do. It requires that you have a positive radius of convergence. But if you have a positive radius of convergence, then you can use this fact, which says that the sum as n goes from 0 to infinity, well, the power series, is equal to 0. Well, let's think about this. The power series has this x in it, so the power series is a function, right? And the domain of that function is all the x's that you can plug in where you get something convergent. So the domain is going to be an interval. It's called the interval of convergence. It's going to include all the points where you have absolute convergence, plus it might include one or both of the endpoints of that interval. So it's a function. And when I say that it equals 0, I mean that it is equal to the 0 function. And I'll just write equals 0 for all x as a shorthand for that. What I'm writing there doesn't mean that it converges for all x and converges to 0, just that where it converges to 0. So it's the 0 function. And that's going to be true if and only if all of the coefficients are 0. So this is a familiar fact when it comes to polynomials, and we use it all the time, like when we're equating coefficients. When we equate coefficients, say, in a partial fractions problem, we're using the fact that a polynomial is equal to the 0 function if and only if all of its coefficients are 0. A mathematically equivalent way of saying that is that two polynomials are equal as functions if and only if they have the same coefficients. And this fact here is telling us that that same thing is true not just for polynomials but for power series as well. Okay, so two power series are equal to the same function if and only if they have the same coefficients, and in particular it's equal to the 0 function if and only if all the coefficients are 0. Okay, another fact here, very useful. We can differentiate and integrate power series term by term. And when we do that, the radius of convergence remains the same. And incidentally, the interval of convergence, which includes all the points there inside the radius of convergence and might also include one or both of the endpoints, the interval of convergence could change. The radius of convergence will stay the same, but what's happening at the endpoints might change. It might be that for your series, it converges at both endpoints, but then after you differentiate it, it diverges at both endpoints. There's no reliable thing that you can say about what happens at the endpoints when you differentiate and integrate. But you can say that the radius of convergence always stays the same when you differentiate and integrate. I'll be doing an example of that here in a moment. And now one last thing. Now this is maybe not a review of something from Calc 2, but a definition that we're going to need when we apply this stuff to differential equations. So here's a definition. A function f is said to be analytic at a point x0 if it has a power series representation centered at x0 with a positive radius of convergence. Okay? So if you have a function f and you want to know if it's analytic, then you have to find a power series centered at x0 with a positive radius of convergence so that that function is equal to that power series, at least as long as you stay inside the interval of convergence. Some examples of functions. We're not going to prove that these things are analytic, so the proof is to just recollect facts that you would have learned in Calc 2. But here's a collection of functions that are analytic, and you can take the fact that these are analytic as part of your toolbox when you're solving problems. So polynomials, the exponential function, sine and cosine, natural logarithm, and ratios of these. All of those functions are analytic everywhere in their domains. So all of those functions, wherever they are defined, they are analytic, and we can take that as a fact as we move forward to use this material. Okay, let's see an example. All right, so the geometric series. So the geometric series, we have an explicit expression for the sum of the geometric series, and that series has a radius of convergence of 1 and is equal to this function when we stay inside the radius of convergence. Now I can differentiate term by term. Now when you differentiate, you have to be careful about the fact that the derivative of a constant is 0. So when I differentiate this series, I want to look at the first term, and if the first term is a constant, then when I differentiate, I have to throw it away. So the first term here is n equals 0, and x to the 0 is 1. That's a constant. So when I differentiate, so here I'm differentiating, that first term, I'm going to have to throw that away, so my new series starts at 1. And then I differentiate each term. The derivative of x to the n is n times x to the n minus 1. I can differentiate the right-hand side, and I have 1 over 1 minus x squared. And that series there also has radius of convergence 1. Radius of convergence doesn't change when you differentiate. I can differentiate again. All right, so on the left-hand side, again, let me check the first term. When I plug in n equals 1, I have 1 times x to the 0. So again, the first term is 1, a constant. When I differentiate, that first term is going to drop away. So my new series will start at 2. And then I differentiate, and I have n times n minus 1 times x to the n minus 2. On the right-hand side, I can differentiate again. I have 2 over 1 minus x cubed. And again, radius of convergence doesn't change. And by doing this, I started here with a series for 1 over 1 minus x and ended up getting a series for 2 other functions. So for example, for any x in the interval from -1 to 1, because the radius of convergence is 1 and the center is 0, I get that 1 over 1 minus x cubed is equal to 1/2 times the sum as n goes from 2 to infinity of n times n minus 1 times x to the n minus 2. Now, that's not quite a power series representation of the form that we looked at. If I scroll back up at the beginning, I want my power series to look like this. Those have exponents n there. Whereas here, the power is n minus 2. So I can make a shift here. And one way to do this shift is to just make a substitution. So instead, for n minus 2 there, let me substitute m equals n minus 2. Okay? And if I solve that for n, that means n is m plus 2. I can make that substitution here, and I'll get the following. I have a sum, and then n is m plus 2. n minus 1 is m plus 2 minus 1, so m plus 1. And then I have x to the m. And I have to think about my limits. Well, when n is 2, m becomes 2 minus 2, so I start at m equals 0. And as n goes to infinity, m also goes to infinity. It's just like making a u substitution in an integral. Now, of course, that index, n or m, it's just a dummy variable. If I wanted, I could change that m back to an n just for consistency. It's not necessary, but it just makes all my series look the same if I put n back in there. And what I've done is going from here to here, what I've done is I've shifted the index of summation. And I've shown you a very algorithmic step-by-step procedure for doing that. And you can do it that way. But in practice, what I do and what I will do in the future in these videos is to just go from the first line to the third line. Just do a shift of index of summation without actually making an explicit substitution like this. But if it confuses you and you want to keep your head straight on it, go ahead and make that explicit substitution, because that's exactly what you're doing behind the scenes when you just jump from step 1 to step 3. So this is called a shift of index. Okay, so those are a lot of things that we're going to be using in the next section. The next section, we're going to be using power series to solve differential equations. And so we need all these tools. Again, go back through this video, find the things there that you don't remember so well, that maybe you didn't learn the first time you took Calc 2 for one reason or another. Find those areas where you need some review and go and find resources and review it. And if you want my help finding resources, I am happy to do it. Send me an email and let me know what you need, and I will help you to find what you need to fill in any gaps and find resources for you to refresh yourself on this material. But it's very important, so don't take it for granted that you know everything about series. Figure out where you need to review and review that. We'll stop this here and make a new video for section 8.3.